Okay, so after looking at the demo of how to do this equilibrium straw lab, we want to look at our data, and then we're going to graph the data so you can understand what's going on there. So let's scroll down here. We want to look at this data, and then we're going to graph it. So first, let's do experiment number 1. So we're doing experiment number 1. Experiment number 1 is how I first did it, where we started with 10 milliliters in the reactant cylinder. So we had a lot in the reactants on the left, and then we had nothing in the products on the right. So what we want to do is we're going to basically graph all of the reactant data, and we're going to connect that with one smooth line. So see how it says connect all reactant points together with a smooth curve. So let's do that. So what you want to do is you're going to start up here at 10 milliliters. For the first transfer really was at 0. You're at 10, right? So we're going to fill that in there. Then after transfer number 1, we were at 7.5. So transfer number 1, you want to be up at 7.5. So put a dot there. And then transfer 2, you're at 6.5. So put one in there. And then just keep going. Once you have all those points for the reactants, you want to connect them together with a smooth curve. And this is really good data. Sometimes there's a few points that are off that curve a little bit, but that's pretty nice. And that's our reactant data. So I'm going to write reactants here. Right? So you started at 10 and it ended up at 4, right? So the reactants ended up at 4. So now we're going to do the same thing with the product data, right? So now do the same thing. You're going to start down here at 0. And let me get and put in all of that data. If you need a little bit more time, just pause the video, but I'm just going to, once I get all those points in, I'm just going to make a smooth curve. And those are the products. I'm going to actually move this and just write. So we have graphed experiment number 1, where we started with lots of reactants and we ended up at a height of 4. Products, we started with 0 products, but we ended up at 6. So that's experiment number 1. So what you want to do is you want to do exactly the same thing for experiment number 2 and plot it out. So again, do one curve for the reactants and one curve for the products. The only difference here is that our reactants are starting down here at 0, right? And then you're going to do 1.4. So connect those reactants together and then do the curve for the products. So why don't you pause and finish that up? Okay, so once you're done plotting all of your data, you should have 2 graphs that look like these that I have here. And what I want you to realize is that in both graphs, the products are at 6 and the reactants are at 4 once it gets to equilibrium. Equilibrium is the part where it's staying constant. So that's at equilibrium. This is staying constant, it's at equilibrium. So that's our definition of what equilibrium is when it's staying constant. Notice the products and the reactants are not the same, right? They're at different heights, but they're all staying constant. So that's what equilibrium means. Make sure you don't think that the reactants and the products have to be the same. So it's not a height of 5 and a height of 5. So we need 5 and 5. So we need to figure out why that is. The other thing I want you to realize is in this data, make sure you had circled fatter and thinner, because remember in both of my cases, I always put the fatter in the reactants and the thinner in the products, and that's what's going to give this data here. So when you do the fatter in the reactants, you always end up at a height of 4, and if you do the thinner in the products, you always then end up at the height of 6, right? So that's always going to happen. Okay, so make sure you also realize that then the only difference is they're ending out the same, but they look kind of different. And the reason they look different is because of whether you start with all reactants or you start with all products. So in the first one, we started with lots of reactants, right? So it decreased down to 4. And in the second one, we started with 0 reactants, and so it went up to 4. So in both cases, the reactants ended at 4, but it just depended on where it started from. That's why sometimes they cross and sometimes they don't. Okay? All right. Now, let's go to the back of the lab and let's see if we can do these post-lab questions together. So here we go. So in this lab, you had 2 different straws, one fat and one thin. In experiment 1 and 2 at equilibrium, the cylinder with the fat straw always had a height of, and what you can do is go back, the fat straw, we always ended with a height of 4. So let's write that in. So height of 4. And that's the height. So I'll put 4 milliliters, but again, it's the height that matters, not the volume. And the thin straw had a height of 6. And you know what? I'm just going to get rid of the milliliters. So height of 4, height of 6. So at equilibrium, the fatter straw had the fatter straw was a height of 4. The thinner straw had a height of 6. So the fatter straw had the lower height and the thinner straw had the higher height. That is always going to be true, and that totally should make sense. Let's draw a little picture. So let's imagine this is our graduated cylinder. And we're going to we had the fatter straw here. So this is the one that we ended with 4, height of 4. And that was the one with the fatter straw. And then the thinner straw, let's make a thinner straw. When it was in the graduated with the thinner straw, you had a height of 6. All right, so this was at 4 and this was at 6. So this was the fatter straw and this was the thinner straw. So what we're saying is at equilibrium, and this is at equilibrium, we always had the fatter straw had a height of 4 and the thinner straw always was the one with the height of 6. So that's what we're saying. So that's how it ends up. So now, why are the heights, explain why, okay, let's read this again. At equilibrium, the heights in the straws were not equal, right? They weren't 5 and 5, they're 4 and 6. However, the heights did stay constant in equilibrium, even though water was continuously transferred. So even though we transferred back and forth between the graduated cylinders, we always had the same constant height. Explain why the heights did constant at equilibrium. So heights were constant because, so let's think about this for a little bit. So you always ended up with a lower height with the fatter straw and the higher height with the thinner straw, right? So what must be true? You keep transferring, but those heights are staying the same, right? So even though you're transferring, the heights are staying the same. What must be true about what's being transferred every time if the heights are staying the same? yes, hopefully you're getting that you're always transferring the same volume of water. So you get the same volume with a height of 4 for a fatter straw than a height of 6 for a thinner straw, right? So you're always getting the same constant amount of water being transferred in those straws. So heights were constant because the volume of water in straws were the same. Transferred. Say transferred. Was the same. For both straws. So that's why the heights are staying constant. It's the only way that could be constant is if you're actually transferring the same amount of water every time. So even though you're transferring, you're still keeping the same heights. So explain why the heights were not equal at equilibrium? So now the question is, well, why is it 4 and this one's at 6? Like, why wasn't it 5 and 5, right? So hopefully you're getting, again, it's really kind of the same reason. The fatter straw, in order to transfer the same amount of water, it has to have a lower height because it's fatter to have the same volume as the higher height for a thinner straw, right? So to transfer the same amount, you need to have different heights, right? Fatter straw needs lower height to transfer same volume of water for thinner straw higher height. So hopefully that makes sense, right? You're always transferring the same volume, but the fatter straw has to have a lower height to transfer the same amount as the thinner straw at the higher height. So that's why you end up at 4 and 6 and not at the same 5 and 5. What would have to be true about the straws to make the heights equal at equilibrium so that you do end up at 5 and 5? Okay, hopefully you realize they would have to be the same diameter straws needed, because then you would have the same heights, you would be transferring the same amount of water at equilibrium. So then you would end up at 5 and 5. And then, so that's the basic concept, right? And this is what was an analogy for a chemical reaction. There are reactions that go in the forward direction and in the reverse direction. And so, reactants go to products, but products go back to reactants. So that's what this analogy is about, is the situation in reactions where you have both a forward reaction and a reverse reaction. So a couple of terms that we're going to end up using is this concept of dynamic equilibrium. And so let's see if we can kind of think of what those terms mean. So what was dynamic about your system at equilibrium? So in other words, what was always happening? So remember, we were at equilibrium when everything stayed constant, right? So this is when you're at equilibrium. Get a different color here. So you might want to mark this. So let's make a nice circle here, a darker color. So let's just make a box, right? So once all of those heights were staying constant, you are at equilibrium because you have constant heights. So here you're at equilibrium. You have constant heights. So what's happening? So even though these are staying constant, you're still doing something, right? You would still be transferring back and forth, back and forth. You're transferring water back and forth with the straws. So what's always happening is water is always being transferred. Water always transferred. So it doesn't stop. Like it looks like it's stopped. Everything's constant, but you're still transferring water. Water always transferred back and forth. So that's what we mean by dynamic. It's not doing nothing, right? You are transferring water back and forth. But what's balanced? Sometimes when you hear the term equilibrium, you think like it's equal. And so I just want you to make sure you don't think that it's equal. Reactants don't have to be equal to products, but all that has to happen is that what's staying constant. That's really what's balanced, is it's just staying constant. And so you have constant heights of reactants and products. And what our analogy is going to be eventually is these heights are going to be our concentrations of reactants and products. Okay, so again, this is an analogy. Our heights are kind of going to be the concentrations. But I just wanted you to see it. The biggest misconception people have about equilibrium is that people think at equilibrium, you would have the same concentrations of reactants and products. So I just want you to realize that that's not true. At equilibrium, we have different heights, but you're transferring the same amount. And so the heights are staying constant, but the heights do not have to be equal. So that's our basic concept that we want to get from this lab. You can now do your homework.